we went over some of practical things of running experiments. But before that, last Thursday, what we were discussing was Q learning, and then we went into actor-critic frameworks, and specifically we were discussing about the DDPG algorithm, right? And the way DDPG works is that there is a policy network which takes the state as inputs and predicts the action, and then there's a critic network, right, which evaluates how good that particular action is given that particular state. And and essentially the way we train the actor is to maximize the critic. So last time we saw a couple of things which could go wrong with the actor critic framework. For the last thing which I want to touch upon is, which is important to note, is what happens if the critic that I'm approximating is far away from the ground truth critic, right? So almost always, if my ground truth critic is q of s comma a, and the critic that I estimate is q of theta q, it's going to approximately be correct, but it's not going to be correct exactly. So because of this approximation, what can happen is that the actor gradients can be noisy, and sometimes the gradient of the actor may not even be in ascent direction. Right? It's because if I'm optimizing a critic and the critic is off, and I take a gradient with respect to that, that might not give me the right gradient with respect to my ground truth critic value. Right? So because we are working with an imperfect critic, the gradient that I am getting may not even be a good direction. So we need to fix this problem. So now there are some conditions under which we can guarantee that the actor critic is going to give us accurate gradients, right? So the two conditions which must hold, or at least it's not a must hold, but if these conditions hold true, we will get an accurate gradient. Right? So one condition is that if I compute the gradient of my action with respect to my critic, it should be a linear feature of the you know of my parameters and the gradient itself, right? So what I'm saying is my critic, the gradient of the critic is linear in the parameters theta q. So if that condition holds true, and other condition holds true where theta q minimizes this particular quantity, right, where epsilon is defined as the error between the gradient of qs comma a with the estimated q function. Right? So if my parameters of the critic satisfy these two conditions, then we are guaranteed an accurate gradient. But the problem is that we never have access to this, right? So we can never, you know, minimize this term explicitly, right? That we cannot do because we never have access to the Q function. Like in practice, we use the TD error, right? Which is when I say Q of ST comma AT is RT plus gamma times the Q value of the next time step. So the theory gives us two conditions under which the gradients are going to be accurate. But these conditions have their limitations, right? For example, the second condition is not optimizable because we don't have access to the ground truth Q function. And in order to satisfy condition number one, there is also a construction. Was there a question? No. Okay. So to satisfy condition number one, there is even a construction of the features that one could use, right? So the features over here, right, can actually be in this particular closed form, right, where the features are defined as the gradient and the action minus the predicted action, right? But again, the problem is that in practice, we don't use linear function approximators to measure the Q value, right? And typically, phi SA is learned using function approximation, right? So I think the takeaway is that there are two conditions under which, if I'm learning the critic, I would get an accurate gradient. But unfortunately, both of those conditions do not end up matching with how real world problems turn out to be. And this problem that the critic is approximate causes a lot of issues in practice. For example, if you ever were to train DDPG, you will find it is very unstable to train. Why is it unstable? Because the gradient that you're getting may not be the true gradient. So sometimes you might be increasing the Q function. Sometimes you might actually end up decreasing the Q function by taking a gradient step. So now there have been different ways to improve estimation of the Q value. Right? So in the previous lecture, we discussed about double Q learning. There are some works which try to measure uncertainty of the Q function. And there are some other methods which are out there. So now what I'm going to describe are like one method which is much more stable than DDPG and tries to get around this problem. And the method that we're going to discuss is called TD3, or twin delayed DDPG. So this method has three tricks. So the one is the double Q learning trick, that we have already seen. The one addition that they have is they use clipping of the Q function. Now, why are they using clipping? Because we were always over approximating the Q values. So clipping is a way to stop over approximation. Right? What do I mean by clip? By clipping, I mean if my value goes above a particular threshold, I will choose my Q function to be that threshold. Right? So it's like if I knew an upper bound on the Q values, I could easily clip them. Right? But sometimes we don't know the upper bound, but still, we can use a heuristic to clip. Now, a second trick that they end up using is what is called as delayed policy updates. So, from the discussion that we had, the instability in Q learning is coming from the fact that critic is approximate, right? And then we are taking the gradient through the critic. So to prevent the critic from being approximate, or to improve the accuracy of the critic, what we can do is we can take more gradient steps for the critic so that it learns faster. And when the critic is stable, only then we take the gradient with respect to the active. So in line with this intuition, what they find is that if you do the Q function update twice as often as the policy update, the training becomes much more, it's much nicer, the way the training works, or the stability of the training is much nicer. And the third trick that they end up using is target policy smoothing, where, so this is again, the intuition for what target policy smoothing is again derived from the overestimation of Q learning. And as we saw in the previous lecture, that one way that Q learning can be exploited is if I use the same Q function to choose the best action and also to evaluate it. So what target policy smoothing does is it adds some noise to the target action to make it harder for Q learning to exploit and over approximate the Q functions. So, with these, three simple additions, the stability of the algorithm is much improved as compared to DDPG. So before I move forward, I'll take a small pause and see if there are any questions. Any questions? No? Does this all make sense?
Could you go over again how the target policy is smoothed in this case?
So you have a continuous action that you are sampling, right? And what you do is that you add some. Suppose I have an action which is the max. So if I differentiate through the critic and find the optimal action, suppose it comes out to be 80. What I'll do is I'll do 80 plus some noise, right? And that noise could be sampled from some distribution, for example, a normal distribution. And then I evaluate the Q value with respect to that, right? So that is how the smoothing is working.
All right. All right. Thank you.
Yeah. Okay, so if there are no more questions, I will move ahead, but I'm happy to take more questions, maybe at the end of the lecture. Then the second algorithm, which is worth knowing in case of continuous Q learning, is soft actor critic, or SSC. So I'm going to describe it at a high level. And then, if we have more time and more interest from the course later on, we will go into more detail about soft actor critic. So the main idea here is that if you look at what the target for the Q function is, we have the reward plus gamma times the Q value of the next state, which is what we are used to seeing. But additionally, they have one more term which encourages the policy to be as random as possible. Right? So this is what is called as the entropy term. Right? So entropy, if you increase entropy, it means that I am asking the policy to be as random as possible, right? While still satisfying the constraints of my Q learning. So the addition of this entropy term again helped with training quite a bit. Why is that? The intuition is that there can be multiple policies which correspond to the same Q function. Right? As we saw in policy iteration and value iteration, that there can be multiple policies which can have the same value function. So instead of committing to one of them, we want to say, well, if all of them are equal, or if all of the policies have the same Q function, then I'm not going to distinguish between them. And this is exactly what the entropy term is doing. So, that's all I will say about soft actor critic for now. And, if you want to go in more detail about this, you know, you can always leave some feedback on the anonymous form, or, in the assignment form. So we are going to get an assignment on Q learning, which will go out today. So you will actually be implementing, tabular Q learning, you'll be doing DQN, and you'll be doing double Q learning and some other bells and whistles. Right? So if you want to learn more about soft actor critic, you can give us feedback on the assignment, or, in office hours, or any mechanism, and we can cover it in more detail. So with that, I will end the lecture on Q learning and switch over to policy gradients. So while I'm transitioning, are there any questions? No? I guess I see a question in the chat. Let me see what the question is. Is there a big difference? Well, those are two different ways of inducing exploration. Now, is there a big difference? I mean, it is, theoretically, entropy is much more well behaved, because if you are, for example, characterizing your action distribution to be a Gaussian, and you say I'm maximizing entropy, it means something, right? In which I'm saying I am trying to be as random as possible. Versus epsilon greedy, you can't really say anything about it, right? It's just a heuristic of how I choose it to be epsilon greedy. Then the second thing is, we cannot really use epsilon greedy in case of continuous actions, right? So entropy, you can think of it as a way of doing exploration for continuous action spaces, right? So either you can inject noise in the form of sample from some distribution. For example, noise could be Gaussian, and we can add that, or we could use the entropy penalty, which has a much more grounded meaning in terms of distributions. Did I answer your question, Gregory?
Yeah, that does. That's very helpful. Thank you.
Okay, perfect. So in this lecture, we have four different goals. So the four goals are: first, we will try to understand policy gradients, which is another class of algorithms for optimizing rewards. Then we will look at the credit assignment problem, and then we will look at a number of variance reduction techniques. Now, what variance reduction is will become clear in the lecture, but that is one of the most significant problem with policy gradients. And in the end, we will look at some asynchronous methods for doing policy gradients. So, let's go back to the reinforcement learning problem. Right? So we want to maximize the sum of rewards, right? And we want to find a policy which is going to perform this maximization. And when I roll out my policy, I end up getting a trajectory which is state, action, and rewards. So now it turns out that instead of doing like actor critic as we were doing, we can directly try to maximize for the sum of rewards. And if I directly try to maximize for the sum of rewards, I end up getting this particular expression, right? Which turns out to be the gradient of the log probability of the trajectory times the reward. Right? But what is R tau? R tau is just the reward of the entire trajectory. So, so, so the high level that we're going to build upon is in actor critic, I have to estimate the critic and then take the gradient through it. Now we'll try not to have a critic, but directly try to optimize the reward function. So now let's look at how this term comes along. But this term is exactly what we'll be calling policy gradients, right? Because this is giving us a gradient with respect to my reward function. So let's look at how does this term comes about. So my goal is to maximize the expected sum of rewards with respect to the policy parameters theta. And for maximization, we can take the gradients and do gradient ascent. So let's write this down. So an expectation can be expressed in the following way. This is just the definition of the expectation in continuous state spaces or action spaces. Now, we can use the Leibniz integral rule to take this differential inside the integral. I can do this. Why? Because my integral is with respect to the trajectories versus my differentiation is with respect to the parameters theta, right? So those are not the same parameters. So I can apply the Leibniz integral rule. Right? Now, what we're going to do is we're going to divide and multiply with the same quantity p theta of tau, which is the probability of the trajectory. Right? And the reason for doing this is because it gives quite a nice, elegant form. Why is that? Because if you look at this term over here, which is gradient of the probability of trajectory divided by the probability of trajectory, this turns out to actually be the gradient of the log of the probability of the trajectory. So this is now I can just rewrite this term as an expectation of the log of the probability of the trajectory times the reward function. So what does this mean? Right? So let's look at an intuitive interpretation of policy gradient. Right? So let's try to understand what is this term doing. What this is saying is because I have to compute the expectation, I am going to first roll out multiple trajectories, and we're going to increase the probability of trajectories that result in high rewards. Like, why is that? Because if the reward is high, and then so I should try to assign a lot of probability to those trajectories. And if I do that, then my expectation is going to be higher. So intuitively, if my trajectory reaches close to the goal, I'm going to increase the probability by more amount. If it is farther away from the goal, I'm going to increase the probability of that trajectory by smaller and smaller amounts. So there's a question about what R tau is. R tau is the sum of rewards. So if we go on the previous slides, R tau is this, the sum of rewards over here. Okay, so this is, intuitively what is happening in policy gradient. Now we can actually go and compare this with supervised learning setup, right? In reinforcement learning, all I have access to are rewards at every time step. Versus if I was trying to do supervised learning to find a policy, I will have states and have access to the ground truth actions, which I would try to mimic. So while policy gradients has this particular form, maximum likelihood estimation has this particular form, right? So in both of them, they're pretty similar, right? You have the same term, which is the log of probability of the trajectory. The key difference is that in supervised learning, the trajectories are pre-given, versus in reinforcement learning, the trajectories are not provided by an expert, but the agent needs to choose its own trajectories. Right? And this is what the reward term is doing. It is helping the agent put more weight on trajectories which lead to higher reward. Right? So it's trying to compensate for the fact that no one told me what are good trajectories, right? So in supervised learning, someone tells me what the good trajectories are, so I can just do maximum likelihood directly. In policy gradients, no one tells me what good trajectories are, so I need to figure them out on my own. So therefore, I'm weighting them by the reward I get for that particular trajectory. So I will, now pause for a bit and see if there are any questions on, what policy gradients are, or, or maybe you want me to go over some part of the lecture more slowly, or, anything that you might be confused about or have a comment. Is everyone on board with policy gradients? Is anything about them, worrying you, confusing you? So this is going to, the rest of the lecture is pretty much going to build upon policy gradients. So if there is something, which you're not sure about, I would really encourage to ask now, because otherwise rest of the lecture might be hard to follow. Okay. Well, I have a question that says that R is just the optimal action for policy theta for each step. I'm not sure, Curtis, what the question is. Can you maybe elaborate?
Yeah, I'm just wondering, so for the maximum likelihood, you were mentioning that you have R, whereas with policy gradients, you don't have it, so you're implicitly just doing this expectation. So I was just trying to better understand sort of like the difference in terms of runtime and like what we're actually computing, like when you operationalize this. And so I was just, is R like the optimal step for the policy? It's the optimal reward you get for an action for a given trajectories?
So R is not the optimal reward. It is a reward that you get from the environment for that particular trajectory. Right? So we never have access to the optimal reward function.
Or not optimal, but just the max for that policy.
So it's not even the max reward, right? If I roll out a policy, right, I get a trajectory. If I execute a policy, I get a trajectory. And I'm just computing the reward I end up getting in that trajectory. Let's say if I execute, does that make sense?
Yeah, it does. Okay. So it's just an expectation over a bunch of different trajectories, but not necessarily, there's no like, you're not doing any max for how you choose a trajectory.
No. I'm not doing any maths on how I choose the trajectory, right? What this will end up doing implicitly is it will try to incentivize trajectories which have high rewards, right? In order to maximize the expectation.
Got it. Thanks.
So there's another question coming in. How do you measure the probability of the trajectory? We will come to it. That's a good question. The second question is, would the policy gradient theorem have an alternative derivation based on discounted state distribution? So there are many possible derivations of policy gradients which are out there. I don't think discounting is going to change much, but I believe you can derive gradients based on the state distributions also. But I think the form is not going to change. The form is going to remain the same. Did I answer your question, Dongchi?
Yes, thanks so much. I think I was trying to connect between the two derivations that I think sometimes I see the policy gradient has been derived, how the lecture has explained. But when I see Professor Sutton's book, the policy gradient was derived using the state distribution. So I was trying to connect the two theorem at the same time.
Yeah, so I think that's an excellent topic. Maybe you can suggest that topic for advanced. So we have 3 lectures at the end of the course for advanced topics.
Mm.
Right. So I think maybe you can put a suggestion for that. And I
Thanks.
think if maybe you want it, then we can cover that in the advanced topics.
Thank you so much.
Okay. So, given the understanding that we have developed for policy gradients, let's try to march ahead and see what are some practical issues which come in when we try to implement this. So, the first issue is as following. Now, suppose I have this white ball, which I want to move to the yellow ball, and I get a reward of +1 if I'm within this blue circle. So now suppose I roll out this trajectory, right? Then I'll get a reward of +1 for this entire trajectory. So now what I will do is I'm going to increase the log probability of each action, right? Because the reward is for the entire trajectory. Right? So what that would mean is that I'm going to increase the probability of every action that I took in this particular trajectory. It doesn't seem too bad because all of the actions were kind of taking you towards the goal. But what about now? Right? In this case, the first action is actually not in the direction of the goal, but I eventually do end up reaching the goal. Right? So if I'm doing policy gradients, then I'm also going to increase the log probability of this action, which is suboptimal. So now, the issue or the question that happens is, I get a reward for the entire trajectory. Now, what actions were the most important for that reward to happen? Right? I mean, maybe this action was not as critical for the reward, right? But maybe this action was very critical for the reward. But right now, I'm going to associate the reward with the entire trajectory. I'm not going to associate it with specific actions because I really don't know how to do that. So this is what is called as a credit assignment problem, or the issue of credit assignment, which is given I get a reward for my trajectory, can I infer or can I say that these actions are the most important actions which led to the reward and the other actions were bad ones, right? If I roll out a trajectory, I get a reward. If I'm doing policy gradients, I'm implicitly assuming that all actions are equally good in that trajectory. Right? So I'll just, let that thought set in. because so this is one of big challenges in reinforcement learning, and also in applying policy gradients or even actor critic. And this doesn't goes away even for the Q learning kind of actor critic methods we saw. And maybe to nudge you a little bit, the question I have is, does this also happen in supervised learning? Is there an issue with credit assignment in supervised learning? Or does this problem not arise in supervised learning? Anyone, maybe wants to type in the chat or, wants to shout out? Or, maybe I can ask, do you understand the issue of credit assignment? Is that pretty clear? Okay, so I'm getting some responses on the chat, right? So some people suggest that since we have tuples of states and actions and rewards, credit assignment is not really a problem, right? So in some ways, what that means is that if I have a state, for every state, I have been given an action, right? And we are assuming, typically in supervised learning, that the labels that I give are good, right? And because that implicit assumption has been made, for every state, we are training on a good label, right? So the credit assignment problem is essentially getting solved by the mechanism which provides the label. The big problem in RL is that no one gives me the label. I need to figure out my own label, which leads to the credit assignment issue. Now, there's a second thought which is coming up on the chat, which is, in image classification, there can be spurious features which can to make a prediction. Right? So now that is a problem at like a feature level. Is saying if I have multiple features which predict the same output, which of those features is important, right? I mean, so that problem happens in supervised learning, but I think the key difference is in the reinforcement learning setup, there is a temporal nature, right? In the sense that I'm only getting, a reward for the entire trajectory that I execute, right? In supervised learning, you'll end up choosing one feature, right? And that feature that you end up choosing could be incorrect, but it will still maximize your training error on that data set. Sorry, minimize the training error on that data set. Right? So the spurious feature will only become apparent when you're evaluating on a new test set. Right? Versus in reinforcement learning, it's not a train or test set issue. Right? The credit assignment will happen at the training time itself. So yeah. So I mean, so I'm happy to discuss this relationship between supervised learning and reinforcement learning, and how the credit assignment between features and credit assignment between actions have similarities as well as some dissimilarities. So I think at a high level, there is credit assignment in reinforcement learning. If I gave action labels for every state, then I have given a good choice of action per state. So therefore, I know for every state what is a good action, right? So that is credit assignment at the label level. There's another kind of credit assignment which is at the feature level, which is what feature should explain the label. Now that kind of credit assignment happens in supervised learning. So think of RL, the problem is compounded. you will have the same problem of choosing good features, but you have an additional problem that we don't even know if the label is correct or not. Does that make sense? Maybe at least to the folks who were writing on chat about credit assignment in supervised learning. Well, maybe we can take this up for discussion if we have some more time after the lecture. But I think it's a good thing to think about, and this is one of the core issues in reinforcement learning. So, okay, so what does this problem of credit assignment actually cause? Right. So what it causes is high variance in gradient estimates. What do I mean by this? Right. Suppose I have the same action. Now, the same action can be part of two trajectories, right? One trajectory which fails and one trajectory which actually goes to the goal. Now, what this means is that I'm going to get conflicting signals about whether this action is good or bad. Right? Because my reward for the left example is 0, if my reward for the right example is 1. And this conflict in gradients is what we call as the variance, right? Because the gradients are now going to have a variance. Sometimes they're pointing in one direction, sometimes they're pointing in the other direction, right? So, I can write down what the variance is, right? Which is as the variance of the policy gradient. And because of the credit assignment issue, there is substantial variance in the gradients. What that means is my training will become unstable, because sometimes I'll be pulled in one direction, sometimes I'll be pulled in a second direction. So one thing to remember, or maybe one, this rule of thumb, or maybe not even rule of thumb, but an anecdote, is that a lot of work in policy gradients is about reducing variance, because that is one of the core challenge which happens in practice. This is something which you will realize as you also do your homework, that there is significant amount of variance. But I hope you're getting an intuition of how fundamentally the problem of credit assignment leads us to having variance. And now what we'll discuss for most of the lecture is how do we reduce this variance so that I can train my policy in a stable fashion. So before I jump into that part, again, I'll take a small pause and see if there are any questions about what do I mean by variance in policy gradients. No? Okay, well, if you have questions, feel free to put them on the chat or, shout out. Okay, so let's look at, some ways in which we can reduce the variance. So one idea is to use discounts. Right? So we saw discounts in a different context earlier. So for example, I have an action which has a reward R. An action which is farther away might have a reward of, gamma times R, gamma square R, or, and maybe this action gets a reward of, gamma cube of R, right? Because this is farther away from my goal, right? So now what that would do is, this would mean that the effect of this action is getting, this action is getting lower reward because of the discounting that I have introduced. Right? So, more formally, I have my policy gradient. Now what I have done is I have put a scaling term over here, or I have modified my reward function to account for a discount factor. And this discount factor pretty much puts in a bias that actions which are closer to the goal are more important and actions which are, which come in much earlier are less important, right? So it's a bias that we are putting, which leads to faster convergence. It is a bias, and it also reduces the variance. And as we discussed earlier, it makes my infinite time horizon work, right? Why is that? Because if my trajectory is very long or infinitely long, then the sum of rewards can blow up. But with a discount factor, it's not going to blow up. So, this is the first trick to reduce variance is the use of discount factor. And it's the typical thing which happens in machine learning. If I reduce the variance, I end up increasing my bias, right? And we will see an example of how the discount factor actually biases the solutions, later in the lecture. So there's a question from Ayush. So Ayush, did I answer your question or is it still unanswered? Perfect. Okay. So now, let's look at a second technique to reduce the variance in policy gradients. But before that, let's try to open up this term, right? So I have this gradient of log of probability of the trajectory, right? And, it turns out that if I compute this gradient, it comes out to this term, which is the probability of the action given my past states and actions. Right? I'm going to simply rewrite this term P with pi, because this is a notation you're going to see in most textbooks. So now what I have done is I have taken the probability of the entire trajectory and reduced it to this. So now there is a mathematical derivation that is there in the slides. So if you look at the PDF, in the end, there is derivation. It's just a wall of math. There isn't really any intuition into why this ends up happening, but this is what one ends up getting. And if you stare at this for some time, you might feel that something is off over here. The reason is, we were taking the probability of the entire trajectory, right? And now what I'm saying is it's only the probability of the action given my past states and actions. That is, there is no dependence on the transition dynamics, which is the probability of going to a future state given my past states and actions. This term completely disappears because this doesn't depend on theta, right? My theta, which is what I'm taking the gradient with respect to, only affects the prediction from state to action. So if you either look in the slides or if you try to just unroll this on your own, you will see this term cancels off. And this is exactly why these methods are called as seems like my slides froze. Can you hear me? Hello.
Mm-hmm.
You can hear me. Okay, something happened with my laptop. Oh shit, my battery became low. Oh, that's why. Okay, hopefully it should be fine now. Okay. So because there is no dependence on this term, this is exactly why these methods are called as model free. Because I don't need to know the dynamics. I can compute the policy gradient without any knowledge of the dynamics. Right? So just to write it again, the policy gradient reduces to this particular form, which is I just need to get the probability of the action given my past states and action. And the other thing to note over here is that the Markov assumption is not necessary at all. Policy gradients can work without the Markov assumption. It's not required. But if we were to make the Markov assumption, we're going to get policy gradients in this following form, right? Which is, I'm just applying the Markov property to this probability of the action given the past states and actions. So for the rest of the lecture, we are going to use the Markov formulation just because it's convenient to write it down. But everything we're going to discuss is also going to hold true for non-Markov application of policy gradients. So now that we have expanded this, let's look at what this term looks like. Right, so I have my term, which is the log of the policy, and I have the sum of rewards. And we're going to ask the question, can we reduce the variance even more? So one observation to make is that for every action, I'm summing the rewards of the entire trajectory. But if I assume that the world, there's some causal structure to the world, right, which is that current actions cannot affect my past rewards, right, then we can make use of that information and change this reward summation to only consider rewards I get in the future, right? Because there's no way my current actions are going to affect my past rewards, right? That's true for most of the world that we live in, right? So if we end up doing that, then we end up removing some spurious terms which were getting added, which have no effect on the action that I am taking. So this is the second idea behind reducing variance, which is by making use of the causal nature of the world that we live in. Any questions on this part? Nope, I don't see any question on the chat. So I'm going to assume that all of you are following this. So now let's see it with the help of an example. What are these different terms doing? So I have the state of an agent, for example, the cheetah agent that we saw in the lectures initially. I have a neural network with parameters theta, which takes the state as input and outputs an action A. Now we can compute the gradient, right, of the action with respect to my parameters theta, right, which is what I am doing, like G1. Then, I apply the action A1, my cheetah goes to a next state, and then we get to A2, right? So what I'm doing is, as I'm rolling out my trajectory, I'm just accumulating my gradients, G1 plus G2 plus G3, which is this symbol T, which means the number of time steps for which I'm rolling out. And this variable N is the number of trajectories over which I'm going to do these rollouts. And for each trajectory, what I'm also measuring is the reward, which in this case is the velocity of the cheetah. So I have the sum of gradients, and I have the velocity every time step, which I'm going to sum up. And then my update equation looks pretty much like normal gradient ascent, right? I have a parameters theta at time step t, is a learning rate alpha, which multiplies by the velocity times the gradients, right? Which is the reward times the gradients that I have. And this is how I get the update of my parameters. So this algorithm that we just discussed is also called as a reinforce algorithm. Why reinforce? Because I'm reinforcing actions which lead to high rewards. So now one question that came up was, how do I characterize the distribution of trajectories? In this form, I only need to characterize the distribution of the action given the state. And so if the action space is discrete, we can use the multinomial distribution to characterize the probability of the trajectory. If the action space is continuous, it is typical to make use of a Gaussian policy. And now, we can go back and see, what is this bias that this discount term actually introduces. Right? So assume that if gamma is very small, right, what might happen? I just try to think of it. I suppose if I make my gamma to be very small, right, what could that lead to? So if gamma is small, it means that only rewards which are very short term in the future matter. And rewards which are much farther away in the future don't matter so much. So, one thing that could happen is if my gamma is small, my cheetah can move really fast now, but it can fall later. Right? So originally, what I wanted to maximize was the sum of rewards, which means that my cheetah should move at a high velocity forever, or at least for t time steps. But because I put this discount factor gamma, I've created a bias. Because now, moving fast for some time is okay. Moving fast for some time and then falling later is okay because of the discount term which is there. And so I have actually changed the kind of behaviors I can expect to get because of this, term gamma. And this is why, and this is what the bias is by putting the term gamma. And, it turns out if we use some advanced versions of policy gradients, for example, to, make this humanoid walk, what this video is showing are some, episodes as the agent is learning, right? So it's iteration number 40, iteration number 80, it's kind of walking. Iteration 160, it improves. And, as more iterations pass, the agent learns this forward walking behavior. So, we are going to, build up towards, what are some changes which go between, going to reinforce to, going to the complete, more advanced versions of policy gradient. But before, I go over there, I'll again take a small pause to see if there are any questions about reinforce. No questions? Does any questions about the discounting? Is the bias clear, the kind of bias that gets introduced? Okay, well, I'll keep an eye on the chat window. So let's, move forward. Now, there's one comment I want to make about policy gradients. I think this is something which, everyone should know. And the question we're going to ask is policy gradient actually a true gradient? Now, just to motivate that or give some context for it, just let's recall the comparison that we had with supervised learning, right? So in supervised learning, I get these state action trajectories, I'm maximizing this maximum likelihood. In RL, I'm doing policy gradients, right? So in supervised learning, one can typically write down a loss function which says that my predicted trajectory should be close to my ground truth trajectory. My predicted trajectory, what do I mean by predicted trajectory? I only mean predicting the actions for every state. Right? So suppose there's a function f which maps my state or it maps my state to my actions, which is a prediction tau hat. So everything is good over here. If f is differentiable, then this loss function is differentiable and we can compute the gradient. And I end up getting a true gradient. Now let's consider the case of reinforcement learning. In reinforcement learning, we are not predicting r hat tau, right? What we are predicting is actually the action, right? But the label that we have is the reward function, right? But we are not predicting this an estimate of the reward function, right? I'm predicting the action. So the mapping between actions and rewards is unknown. Right? For example, I don't know what the game score is unless, I don't know a parametric or even a non-parametric, I don't have the knowledge of the mapping a priori from the state, from the action I take to the reward I get. It's something I can observe, but I don't have the functional form of it. Right? So, if I don't have a functional form of it, one thing we can do is we can use black box optimization, which is finite differencing, which is a well-known method to use if the connection between AT and the reward is a black box, something which is unknown to us. But how would we use black box optimization? Right? So implicitly, we can think of that the reward function does depend on the parameters theta. Because if I choose a good set of theta, I will take good actions, which is going to lead me to higher rewards. Right? So let's try to write down the gradient of the reward function by doing finite differencing. Right? So what I'm going to do is I'm going to write reward theta plus delta theta minus r of theta t, which is the definition of finite difference. And the question I'm going to pose is, can we actually do this? Is this a valid, is this an operator that we can evaluate? Or is this an operator that we cannot evaluate? Any feelings, or anyone has an opinion on this? Doesn't it? Yes, I get one comment from Dhruv says, doesn't this depend on us being able to control which state we are in freely? Right? I think you are spot on. So what that means is, so suppose if I have to evaluate the reward at theta plus delta theta, that means that first I will have to roll out a trajectory from state ST with parameters theta. Then I need to reset the state again back to the same one. And then I need to roll out the policy with parameters theta plus delta theta. Right? This is something which we cannot do unless we can reset the world, right? But resetting the world is something which is not in our control most of the times, which means it's very hard, or it's not possible to compute even this gradient through finite differencing. Right? So it turns out that policy gradient is actually not a true gradient. It is optimizing the sum of rewards in a way, but it is not a true gradient because I cannot evaluate gradient through the definition of how I write a gradient. Right? So it's at most a heuristic. Now, if you want to go into more depth, here's an excellent paper whose title is Policy Gradient a Gradient? And I encourage you to read this. So if there are any quick questions, I'm happy to answer them now. Or otherwise, we'll move ahead to our discussion of reducing variance. No? Okay. So until now, we have looked at two ways of dealing with the variance problem. Right? One is causality, and the other is discounting. Right? So let's look at some more methods. So recall the intuitive interpretation that we had of policy gradients was, if I have a trajectory with high rewards, increase its probability. If the rewards are lower, don't increase it. Right? To say it in a different way, this is a visualization which shows that I'm increasing the probability of trajectory depending on how much reward I get. So one thing you will notice is that irrespective of how bad the trajectory performs, we are always increasing the reward. And if the rewards are positive, then even if I get, a reward of 0.01, I'm always increasing it. You know? Maybe instead of doing that, what I should do is I should only increase the probability if my reward is better than the average reward, right? And maybe this can reduce variance. So, let's see if this is actually true, or if this intuition can help us reduce the variance. So what I'm going to do is I'm going to have my policy gradient term as I had before, and I'm now going to subtract some constant, or not constant, but some term b from it. And the first question is going to be, can I actually subtract something from the rewards, right? Can we actually do this mathematically? Turns out that yes, we can do it if b does not depends on the parameters theta. Now, what is the proof for this? We will do this in the homework. You'll see how to prove this. It's quite straightforward once you end up deriving policy gradients on your own. Okay, so we could do this, but why should this actually help? Why should the variance of the term, which would have minus b, should be less than the variance without subtracting this term? So what we know from mathematics is the variance of two variables x minus y can be written in this form. Now the variance of x minus y is less than equal to variance of x. If the covariance of x comma y is much larger than the variance of y, right? Then this condition will hold true, right? And when will the covariance be large? When x comma y are correlated. Right? If x comma y are correlated, my covariance is going to be large, and therefore I can get this variance reduction. So now consider if we use my baseline as the expected sum of rewards, which is what the intuition was, which is if I am subtracting the average, if I'm only going to increase the log probability if my trajectories are performing better than average, then that can reduce variance, right? I mean, it will end up reducing variance because of the argument that we just saw. Right? Well, then you can say, well, I came up with this intuition, but is there a way where I can be mathematically precise and actually derive what the optimal baseline is going to be? So can I actually optimize for the variance? Right? So can I actually say this is the variance, and I want to find the b, which will minimize the variance of my policy gradients? So it turns out that yes, one can. So the reference which I have in the bottom, which you can look at. And if you find the optimal baseline, it turns out to be, b prime is a weighted sum of rewards, where the weighting comes from this term gt square. It's a weighted trajectory reward, where gt is nothing but this term. It's a gradient of the log probability. So it turns out this is the optimal baseline to reduce variance. But in practice, people end up using the expected sum of rewards, which is also the value function, right? So it's not necessarily the best choice, but a choice that works well in practice. Okay. And so baselines are present everywhere in policy gradients. Why? Because they reduce variance. Any questions on how baselines reduce variance? No? Okay, well, then let's march ahead. So let's put it all together, right? So what we saw is that, my baseline could just be my value function, right? My value function is the expected sum of rewards. So I'm just going to replace it by the value function. You can say, how do we get this? Using value iteration. We'll see this in more detail very soon. right? So now, let's consider this term again, right? Just to gain some more intuition into what is happening. Right? So what is happening is I start from a state S0, I roll out some trajectory T1, some trajectory T2, and so on, and I get, these n trajectories. Now, the first question is, why are these rollouts different in the first place? Right? I mean, we have discussed this because my policy could be stochastic, my environment could be stochastic, or my rewards are stochastic, right? There are multiple reasons why, even if I roll out the same policy, when I say I roll out the same policy, I mean I execute the policy with the same parameters theta, I might end up following different trajectories. Right? Now, if I want to reduce the variance, right? Now, what is one thing I can do? And one thing I can do is I can try to increase the number of data samples I have, right? So we know from statistics, the greater is the sample size, the better is going to be my estimate of the quantity of interest, right? So increasing n can also reduce variance. This is one reason, why we massively parallelize data collection when using policy gradient methods is so that we can, you might have, like 20 workers or 30 workers collecting data in parallel, and we can pool all of that data. Why? Because it's going to reduce my variance and make my training be much more stable. But this is exactly the kind of things, which we can't do on the real system. I cannot massively parallelize data collection. But then you might say, well, I cannot parallelize data collection, but what if I use some of my past data? Right? Can I not use my past data instead of collecting new data? Turns out that with policy gradients, we can't. Why? Because the gradient is with respect to current parameters theta. Right? So what we need is we do need data from the current policy. And this is why these methods are called as on-policy learning. Right? And these tend to be sample inefficient. Exactly because of this nature, because if I just look at the math tells me that I must take my data or collect my data from my current policy. I cannot just put in data from some other policy. Otherwise, the math is not going to work out. Right? So sometimes there's a trick that we can use, which is importance sampling. But it turns out that importance sampling can become very unstable, and practically it is quite non-trivial to make it work. So usually, people would go for off-policy methods if they, or like Q-learning based methods, if they want to use past data instead of trying to do, importance sampling with like an on-policy algorithm, right? It's not that no one does it; it's just that it's far more common to go with Q-learning instead of um, doing importance sampling. So, I mean, one way to understand is importance sampling increases the variance. Now, this is again a slightly more advanced topic, which, again, if you want to learn more about, I think, chime in your feedback, and we'll try to cover some of it in some of the advanced RL topics. So before I move on, any questions on why policy gradients is on policy? No? Okay. Okay, so now, now let's look at this term, you know, once more. Right? So what am I doing over here is I'm trying to estimate the sum of rewards. Right? So the one way to estimate the sum of rewards is to do a Monte Carlo estimation, where I just sum the rewards. But I can compute this in a different way also. I could say, well, this is my RT prime plus gamma times this term. And this is actually nothing but my value function, right? This is what we have seen before. So I could use two ways to estimate the reward. Either I can estimate it directly by accumulating the sum of rewards, or I could predict the value function, right? Just remember what we were doing with actor critic, that we were using a critic to predict the Q value. Right? Similarly, you can use a critic to predict the value function. So now what ends up happening is this does a trade-off between variance versus bias. So why is the variance less on the right? The variance is less because my value function of the next state is not going to depend on the rollout that I'm making. Right? Whatever states happen after st prime plus 1 are not going to affect the value function v. Versus if I'm doing the sum of rewards, it's much more trajectory dependent what this value is going to be. And so therefore, the variance on this term is higher. But then why is the bias over here more? Because this value function is approximating the true value function, right? So it's an approximation. It's not the ground truth value function, and therefore it is biased. Right? So essentially, so now instead of choosing between variance and bias, like which one should be used? Should we use the left one or should we use the right one? It turns out, we don't have to make an explicit choice, right? There are ways to resolve it. And before we go on resolving it, let's consider the second option for a moment. I'm going to write my reward function plus gamma times the value function minus b of st. Right? And this is just the critic. So the critic is very similar to what we discussed in Q learning, and we can learn it using a version of just backing up my value functions. This is what we saw in Q learning, right? That we could approximate the value, or I can estimate the Q values by performing this update, right? When I have my old value plus alpha times the target, right? The target is RT plus gamma V old is my target, and this is what my old value was, and I'm going to add the difference between them. Right? So I have my new estimate using the backup term, and this is my TDL, right? Just repeating those things over here. Right? So what this means is that now, let's look at this term over here. Like this is R plus gamma times the value function, right? I'm just going to open up the bracket so it looks like the following. Now, one second, it seems my charger. So now, this term is nothing but my Q function. And so it turns out that if I am using my critic to approximate the sum of rewards, then policy gradient starts looking like I'm estimating the Q value, and I am criticizing my log probability term by the Q value. But then also I have the baseline term, which is my V of S. This is my Q value function, and the subtraction between them is the advantage function. So we have seen the advantage function before. We saw this in context of dueling networks, when we were saying how we can expand upon DQN to deal with a large action space. So this is what leads us to advantage actor critic methods of doing policy gradients. So just to recap what happened, we started off the lecture by saying I'm going to sum up rewards, and that is how I'm going to estimate R of tau. Right? And then we looked at policy gradients, we looked at some variance reduction techniques, and one of them was introduced as baseline, which is over here V of x. Right? Then we said instead of doing the sum of rewards, which might have a higher variance, I can instead trade it off as something which has a bias but lower variance, which gets me R plus gamma times V. Now, if I just open these terms and rewrite them, it ends up being just an advantage function. Right? So intuitively, what the advantage function is saying is that taking an action A, does it yields me higher reward than the expected action is going to yield me, right? So it's the same intuition. I'm only going to increase the log probability of an action if it is giving me higher reward than the expected reward. So if you can compare the first term with the second term, right? The only difference is the term R tau has now been replaced by the term of advantage. Everything remains exactly the same. So you can think of, instead of critiquing my trajectory by the reward function, I can now critique it by the advantage. Why by the advantage? Because it has the baseline intuition in it. Right? So this is what is also called as the advantage actor critic, or A2C. Now, instead of explicitly trading in the bias and variance in the way we traded, right? I just used, instead of the sum of rewards, I just use RT plus gamma times V of this term. But I could expand my reward function for k steps where k is a variable. Right? So if I expand it only for one step, I call it R1. If I expand for k steps, it's RK. Right? So R1 is going to have the least variance and the highest bias. R infinity is going to have the highest variance but no bias. Right? So as k is going to increase, I can smoothly trade off between bias and variance. So now, instead of choosing any one k, what I can do is I can average over all possible k's. So if my trajectory is length t, I can average over all of those trajectories with some parameter lambda. And what I can now do is I can replace this term with my average. So I end up getting my critic as this new term, which is trading of bias and variance, and then subtracting the baseline from this. And this is what is called as generalized advantage estimation. Right? So what we saw first was advantage estimation. And now what we saw is how we can perform better bias variance trade-off in the computation of the advantage itself. Any questions over here? None? So either all of us, either everyone is with me or I have lost everyone by now. And since I can see no faces, I have no idea what happened. But if there are any questions or comments, that will help me know. Is everyone with me? Then maybe you want to chat. Maybe you want to just type in yes or no. Or just say out yes or no, or maybe do a thumbs up, thumbs down. No, no reactions. Oh. Okay, well, okay, seems like this some positive, but it might take, yeah, so I think this is a lot to process. And, hopefully I've communicated the main ideas over here. We will try to see if we can, yeah, I mean, we will put some pointers so that you can read this in more detail, and maybe also provide with, some lecture notes to help you out. But hopefully this is giving an idea of what the variance trade-off is and how we are. So if you look at, all the things that we have developed are pretty much trading off or are trying to resolve the variance in the problem by trading them off with bias. So in the last 2 minutes, what I will cover is asynchronous methods. The intuition again is very straightforward. So until now, what we have discussed is, we have one worker which is collecting data. I have my state S which goes in. I take my action, and I am training this one worker. Instead of training one worker, I can have a second worker. I can have n workers training simultaneously, right? And all of these workers are, sharing the same parameters theta, right? So I have the same parameters, but think of it, I'm running the same environment in n different CPUs, right? And then I'm going to collect, and each CPU is training on its own independently. And the question that we're going to ask is, what's the advantage of n workers? So it's something which, I will leave you to think about. Right? Is there, there is an advantage, obviously, because the question is, what's the advantage of n workers? Right? This will lead us to the algorithm called asynchronous advantage actor critic. So, if you've not seen the lecture notes, or sorry, if you've not seen the slide PDFs already, maybe not see it for some time and try to think about it, if there could be an advantage to having n workers. So I think next, so the coming Tuesday, I believe, is an institute holiday, so there is no lecture. So we're going to meet on coming Thursday. So with that, I will stop and take any questions. So